Yeah, so welcome to today's plenary talk. And our speaker is Professor Marios Polycarpou. And he is the recipient of the 2024 IEEE Frank Rosenblatt Award. And so the past president of IEEE, Professor Saifur Rahman, will present the award to Marios. So before I invite Professor Saifur Rahman, I will briefly introduce Professor Rahman. So Professor Rahman is the founding director of the Advanced Institute at Virginia Tech, USA, where he is the Joseph R. Loring Professor of Electrical Computer Engineering. He also directs the Center of Energy and the Global Environment. He is a Life Fellow of IEEE and an IEEE Millennium Medal winner. So he was the 2023 IEEE President and CEO, and he is now the past president of IEEE. Yeah, so please, Professor Rahman. Welcome.
Ohayou gozaimasu. Good morning, everybody. I'm honored to be here today for the very special occasion to represent the IEEE Board of Directors for this award ceremony. This award is sponsored by IEEE Computational Intelligence Society and recognizes outstanding contributions to biologically and linguistically motivated computational paradigms and systems. For the 2024 award, right? This is 24. 3, that's what I thought. Is it 24? 23, I am honored to recognize IEEE Fellow Marios Polycarpou for contributions to the theory and application of neural networks and learning systems in monitoring and control. Professor Polycarpou is a professor of electrical and computer engineering and the director of the KIOS Center of Excellence at the University of Cyprus in Nicosia. For more than 30 years, Professor Polycarpou has pioneered the development of neural network-based fault monitoring and event detection. Its wide applications in today's monitoring and control systems makes reliable operation in diverse application domains. Professor Polycarpou's research on intelligent monitoring and control has had long-lasting impact on numerous applications, including water distribution network, robotic systems, smart buildings, automation healthcare, smart grid, and transportation. From water to electricity, everything is in between. His work on neural network-based adaptive control methods has transformed the field and opened new ways for designing neural control systems with learning capabilities for uncertain dynamical systems. He also initiated an entirely new approach to using learning systems methodology for fault diagnosis. First developed in 1994, Professor Polycarpou's approach is now important in the Internet of Things and cyber-physical systems, where faults can heavily and subtly affect application performance. On behalf of IEEE Board of Directors, my pleasure to recognize IEEE Fellow Professor Marios Polycarpou, the recipient of the 2023 IEEE Frank Rosenblatt Award. Professor Polycarpou.
Okay, so now welcome, Professor Polycarpou will give the talk. Yeah.
Okay. Okay, good morning, everybody. First of all, I would like to thank IEEE for this tremendous honor. I'm very, very humbled and honored to receive this award, which especially given the names of the people that have received it in the past. And I would also like to thank the organizers of the conference for the invitation to give a keynote plenary speech, and also to congratulate them for a really wonderful conference organization. I think it's really an exciting time to be working in the AI area in general, and there are so many things going on, and this conference kind of brings together some of the best work that is going on around the world. Before I start my presentation, I wanted to say something about Frank Rosenblatt. So Frank Rosenblatt was a professor of psychology, actually, at Cornell University. And he's considered as the father of the perceptron, which is one of the first models of neural networks that that has led the way to some of the things that are going on today. And if you read the quote from him from 1958, you will see that he kind of predicted some of the things that would be coming up. It just took 50 years to get there, but we are getting closer. And Frank Rosenblatt was actually, so if you look around, all the pictures of him he looks very young. And the reason is because he died young. He died at the age of 43. Actually, he died of a sailing accident on his birthday in 1971. But he was one of the leaders in the area, and some of the things that we now have in terms of computing power, they had like you see in the picture, like a 5-ton machine from IBM and giving cards as inputs in order to try some of the learning algorithms that were developed by Rosenblatt. So it's a great honor to receive the Frank Rosenblatt Technical Field Award. So before I start, let me just say that I'm going to be using the terms artificial intelligence and machine learning and computational intelligence kind of interchangeably because it just makes it too difficult to say one or the other. And I think if you look at the definition of artificial intelligence in the Oxford English Dictionary, it kind of captures pretty much everything that we do. So I think it's okay to be using this, and also the popular media is using this term. So we can be using either one, even though I understand that some of the algorithms may be more machine learning rather than AI, but let's not get stuck on that. And I hope that's not the most controversial thing that I will say in my presentation today. So I would like to make a distinction on where the data comes for AI. So on one hand, in some applications, the data collected is from cyber physical systems that have their own dynamical behavior, and for example, mobile robots, water distribution networks, energy systems, chemical plants. So they are a lot of the times large-scale systems or that have their own dynamics related to that, and we get data and we process this data and learn some things in order to make this operate better. On the other hand, we also have applications where the data doesn't really come in from such systems, like, for example, predicting the prices of housing, large language models, handwritten character recognition, image processing, and things like that. And in both cases, we can think of the data as coming as being offline. So we collect the data, we go to the lab, process the data, come up with some algorithms, or we can think of in some applications, having it online and work with that. In other words, the learning goes on while the system is actually operating. So in this presentation, I'm going to be focusing on the first type of applications. And I will try to give some examples and mention some things so that these are actually, you will see some of the reasons, some of the intricacies by the fact that where the data is coming from and the fact that these applications have their own dynamics, they have their own feedback loops, their own decision-making methods, and the AI comes on top. So a lot of this goes on to, and I'm not saying some of the other applications are not important. I'm just saying, I'm just focusing on this class of systems, keeping in mind that some of the other techniques like an image processing, large language models can indirectly be used also for these dynamical systems that I'm going to be talking about. So this is an outline of my presentation. I'm going to first talk about how do we model these cyber-physical systems, this cyber-physical world out there, and then I'm going to discuss the issue of resiliency, which I think is a critical issue and is going to be a key part of this presentation. Then I'm going to discuss about fault-tolerant systems and fault accommodation, and also talk about cyber-physical security and finish with some conclusions and some take-home messages. So the cyber-physical world consists of things that they have physical parts and cyber parts, and these systems are actually complex and getting more complex because of the Internet of Things, because of adding things to it, because of the interconnections and the interdependencies that are associated with them. So this, a lot of the times they have embedded software and hardware. So they have the hardware components and the algorithms be together. And there's a trend towards making these systems more automated and more autonomous. So just to give you an idea of what I'm talking about, let's see some examples of these cyber-physical systems so that we see what we have in mind. So the smart energy systems is one example where you have different components. You have power generation, you have renewables, you have different transmission lines, and there's decisions to be made in order to optimize that. You have pricing policies and so on. So this is a large-scale system with many sensors, many actuators. It has its own dynamics, and And we want to make this system smarter using these machine learning and AI techniques. Another example that we are working and other people are working on is the urban water systems. Again, here you have reservoirs, you have pumps which are connected to the electricity. You have chlorination of the water in order to make it cleaner for people to drink. You have sensors measuring flows, pressures, the quality of the water, and so on. So again, these are large-scale systems. We have cooperative robots, and when I say robots, they can be ground, they can be drones, they can be air vehicles, and or underwater vehicles. So again, these are examples of the real world where algorithms are being applied to. You have intelligent transportation systems, which is an area that is actually changing significantly in the last few years. People are talking about connected and autonomous cars, and definitely AI is going to play a key role in it, and some of the learning algorithms there. We have chemical plants, we have smart buildings. So you get an idea. So this, what we mean by complex and actually getting more complex. And so if you look at these systems, the cyber-physical world is at the same time exciting, but also a bit scary, because these systems are critical for our everyday life. So we have to make sure that they operate not 90% of the time or 95% of the time, but they operate continuously, and they are large scale. It's very hard to get all the information that we need. There's a lot of uncertainty associated with it. So this is why I want to make this distinction about the data that we are using and the algorithms that we are using. The other thing is that these systems already exist, and they have their own dynamics. People are studying them, chemical engineers and mechanical engineers and electrical engineers and environmental engineers are studying these things. So the issues of intelligence comes on top of that, and I think this is important to keep in mind. So how do we bring together these two components, keeping in mind some of the intricacies of the issue? So before we go on, let's talk a little bit about how we can model some of these things. And there's different ways to model, but I want to keep it a little bit at this cyber-physical level, and look at it at one layer. What we have the physical part, which are the actual system. The sensors are usually physical components. The actuators are physical components. And then on top of that, you have the software, the algorithms, which are usually the controllers, the monitoring algorithms, and so on. So you can think of it as having these two layers, and you can see the white arrows indicate the interconnections between different subsystems. So on one hand, you can say, well, let me try to model this water system or this energy system as one system and not as connected subsystems. But in practice, these are large-scale systems. It's very hard to do that. So a lot of the times, it makes more sense to look at it as different subsystems that are interconnected. Some of the interconnections are weak interconnections. Some of them are strong interconnections, and that makes a big difference. And on top of that, you have the algorithms, you have the software, and this, or you can think of those as agents, and some of it, there is communication between them. So if there is an interconnection between two subsystems, it makes sense for their agent that is monitoring and controlling them to also communicate. And those communications are indicated with the black arrows. Now, so this looks a little bit different than what we see as a diagram of a large-scale system. And if we zoom in on one of these subsystems with its own agent, let's look at this one, for example. If we zoom in on this, we're going to get something that we are more familiar with, where we have the actual plant, the system, where we have the sensors, and the actuators. So this is the hardware, the physical component. And then on top of that, where we have the controller, the K, and the monitoring agent. So you can see what, and these receive information from other agents and send information to other agents. Not everybody to everybody, but to neighboring agents. And then you see the white arrows, which indicate the interconnections between these subsystems. So this type of systems, this is what we study a lot of the times when we think about cyber-physical components. So you can think of this as a single entity, maybe with many sensors and many actuators. Now, if we were to model this would have different components. And on the first line, we see the local known dynamics, which could be nonlinear. In general, is nonlinear. You have the interconnection dynamics, and then you also have all the terms that you don't know about. So this is the difference between the real system and the model that you have. And then you also have the output equations, which is a function of the state and maybe measurement noise and so on. So this type of, so this is how we model these systems, and even before the introduction of machine learning and computational intelligence, some of these techniques. So these equations are maybe differential equations, maybe differential algebraic equations, maybe partial differential equations, sometimes in a lot of these applications you have dedicated simulators that provide this information. However, even the simulators, they may not tell you what is behind the simulator, but there are a lot of the time some equations or some logic functions or things like that. So this is the part that we know. And unfortunately, these models are not correct. So the real world and the mathematical models are not the same. If they were the same, there would be no need. If we had perfect models, there may not be a need for machine learning. There may not be a need even for feedback control, because we would know exactly what the model is, so we can just choose the input that would cause the output to be whatever we want. The whole thing that makes the feedback loops and the intelligence is based on the uncertainty in the system. And a lot of the times, the uncertainty may be small, so we may have parts that we don't know that are not very big. but a lot of the times there's significant uncertainty. And as the systems become more complex, it becomes harder and harder to obtain these models. The other thing is, even if we were able to obtain, to receive some kind of extensive simulation, extensive experimental work, and get a good mathematical model, a good simulator, it's not necessarily true that this model, after operating for 1 or 2 months or 6 months or 1 year or 10 years, is going to remain the same. So things change. So the uncertainty is a big part of what we have to deal with. So this uncertainty kind of motivates a lot of the work on feedback control, as well as intelligence systems and so on. And when we think about it, don't think only of the single agent one, think of the whole thing. So we have a bunch of subsystems that are interconnected. They are monitored and controlled by different controllers, and each one of them may have its own uncertainty that we don't know about, and then we are trying to design systems that operate and do what we would like the system to do, to operate safely, efficiently, environmentally friendly, and so on. So the objectives are also, so this is the situation. So it's a very difficult problem, and you can look at it in different ways. So you can say, well, let me do the best I can with the models that I have, and then the uncertainty I can treat as something extra, try to make the design robust with respect to this uncertainty. So these are the model-based design methods, and these are the methods that people have used for a long time, especially in systems and controls, model-based approaches. On the other hand, you can think about, let's forget about the models, since they are not accurate anyway, and look at and just collect a lot of data. Let's say we can collect as much data as we want, which it's a big if. It's not a very good assumption, but let's say if we could, and based on this data, design algorithms that are and we can use a neural network, or we can use some other techniques in order to do that. And these are data-driven methods, last, we can use a combination of the two. So the combination of model and data-driven methods, and there's a lot of examples of that. For example, in incorporating learning in model-based. So one approach is to take the model-based approach, the algorithms for control and so on, and put learning in there, incorporate the control, the neural network in the feedback loop. Another way is to take machine learning methods and try to incorporate models, physical models, into that. So these are physically inspired, what are called physically inspired learning and so on. So these are the two approaches. There's some other approaches, reinforcement learning and approximate dynamic programming, and I'm giving some references of some of the work that has been done in this area. So in my opinion, this is the direction to go. I don't believe in the first two. Model-based approaches are not enough anymore because the systems are just too complex. unless the system is simple enough that you don't need these advanced techniques. And also data-driven design methods are not enough. If you know something about the model, it's very useful to be able to use that. So this combination of model-based and data-driven approaches is the direction to go, at least in my opinion. But at the same time, I feel that we have not yet reached some, so a lot of the techniques are kind of ad hoc, trying to fit whatever we know into and bring something new rather than design something that is truly bringing the two components together. And so I think there's more to be done. And the other thing that I wanted to mention is the idea of digital twins, which I think is an idea that is gaining a lot of ground and is something that the industry is very much interested in, because it's something that everybody can understand. And the idea of trying different things, you have a digital twin of your real process, you try different things out and see what works and bring the two together. So I think the digital twin is really a combination of this model-based and data-driven methods with online capabilities that improve it over time, and then you can run different what-if scenarios in order to see what you can do. I think this is something that the industry is very much looking into, and is something that the universities can provide more techniques and build on that. So in view of all this, I want to discuss a little bit performance. So for a long time, when academics write papers, they look at some of the components and how they work. They look at the tracking error. They look at what I'm trying to do, and then they say, okay, I have 95% performance rate and so on. And some of them is based on some nominal conditions, and some of it is incorporating some uncertainty into the system. Now, so most of the work has been dealing with performance under nominal conditions and performance in the presence of uncertainty. Now I want to mention the situations where the uncertainty is not the measurement noise, it's not some error in the modeling, but something that happens in the system like a fault or like a cyber attack, which is something a lot more serious than just the issue of robustness. And this leads us to the direction of resilience. So these are events that may not happen very often, but when they do happen, they have a big impact. Think of, for example, like the COVID pandemic. It doesn't happen every day, but when it does happen, it has a major impact in our everyday life. So resilience is important because if you design a system that is perfect, when all the sensors are operating fine and all the actuators are operating fine, and you have some uncertainty, and you have addressed that as well, but what happens if 1 or 2 or 5% of your sensors are giving wrong information and you don't know about it? This may lead to wrong decisions, and this may actually escalate to a catastrophic failure. And we have, unfortunately, examples like this in aircraft systems, and which get a lot of attention because, of course, humans are involved, but there's a lot of things like this in chemical plants and so on. The other thing that is important, as the world is becoming more connected, a fault it will not necessarily stay in one place. So a local fault is not necessarily going to stay where the fault occurred, but because of the interconnections, it may actually propagate into other spatial domains. And in the power systems, there's an example. Well, there's many examples, but there's one that comes to mind where a local component failure in Germany actually, because of the interconnection of the power grid, propagated all the way to blackouts all the way to Spain. So this propagation, which a lot of the times we don't understand it that well, is crucial in a distributed systems. And the other thing is the whole idea of automation and autonomy relies on trustworthiness. Everybody's talking about trustworthiness in terms of the AI. You know, do we trust what we are getting? But trustworthiness is important for all automation procedures. Every time we get on a plane, we trust that the automatic pilot and, of course, the human knows what they are doing, and we trust the automation process to take us where we want to go. Now, if due to some faults this is not valid anymore, if people stop trusting that, then that's a big problem. So resilience is very important, and it's very important to be able to handle low probability, high impact events. And maybe some of you have read the book by Nicholas Taleb about black swans. So these are situations that they don't happen often, but when they do happen, they have a big impact. And sometimes it's positive, sometimes it's negative. In our case, we're talking about some of these negative events. So one of the things that we need to do is we need to find ways to address these situations because even if they don't happen very often, it's something that can have a major effect. So what can actually go wrong? So if you have a system like the one that we described, you can have a fault in the plant, the system. You can have an actuator fault. You can have a sensor fault, especially nowadays with the Internet of Things. We have so many sensors, cheap sensors. It's quite common for some of them to give wrong information. So, so it's very important to be able to address those. We can have communication faults, communication between the controller and the system. We can have between the sensor and then also between subsystems. You can have controller faults. So controllers is really an algorithm. If there was a mistake, in the development of the algorithm, and there's a software code that is not completely correct, this may cause a lot of trouble. Usually this is something that is at the beginning of the operation, not something that changes over time, but it may be something that changes over time. And finally, I want to bring the attention to another class of risks associated with malicious events. These are not faults that they just happen by itself. They happen because there's some people behind it which are causing the fault. And we can think of cyber attacks, which are, they can attack one of the sensors and send wrong information, or the communication link and so on. or we can think of physical attacks. For example, if someone was to contaminate the water in a water distribution network, it's an important thing, but it's not a cyber attack. Right? And those are the things that we want to be able to use our sensing information and our smart algorithms in order to be able to detect, to isolate, to accommodate as quickly as possible. So in situations like this, what can we do? So the first thing that we want to do is that we want to be able to detect that something is wrong. So the event detection is the first step. And most of the research in this area has been dealing with event detection. The other thing that is important is event isolation. There's less work on this, and this is something because a lot of the times in the past the systems were very simple. Isolation was not a critical issue. But however, as systems become large-scale and interconnected, where is the fault is very important. So the event isolation, and you can think of a scenario where you have hundreds or even thousands of sensors, and you have like 10 or 20 of them that are faulty. And the question is, which 10 of them are faulty? Okay, very difficult problem, and that's where data-driven methods, machine learning and AI can actually help in situations like that in combination with the model-based approaches that we are talking about. The third thing that we want to do is we want to estimate what is the risk associated with it. Is this something very serious? Do I have to shut down the system, or can I just wait until the next maintenance period in order to address this? In the area of risk assessment, especially real-time risk assessment, there's not much work at all. So this is a new area. Most of the research has been dealing with event detection, actually, and fault accommodation, which is the last one. So the other thing that I wanted to mention is that how do you address this problem? Traditionally, these algorithms have been addressed in a centralized way, so where we have all the information coming into an algorithm, process the data, process what we are getting, and make decisions about whether there are faults or whether the system is operating safely or not. As the systems become larger, I think we have been moving a little bit in the direction of distributed diagnostic methods, and I think this is very important. And I think this is one of the directions that we want to move more into. The other thing is, how do we address these issues? One way is to address them in a passive way. In other words, we design a system a priori that can address not only nominal conditions, not only uncertainty, but also faults. It's like designing something that is robust enough to address situations like this. And the more active way is to go through the detection, isolation, and address that on a case-by-case basis. And I think, again, a lot of work has been on passive diagnostics. I think the active one requires more attention. So I just wanted to mention that these systems, as they become more large-scale, the distributed fault diagnosis becomes more important because of scalability issues, because of the ability to isolate fault. Because if you work at a local level, then you already know that the fault is either here or it came from one of the neighbors, rather than to have to look in the whole system to see where the fault is. So the distributed approach is something that is, so the more research is required, especially in distributed active event diagnostic methods. And so in order to study these resilience issues that we have been talking about, especially in large-scale cyber-physical systems, we need expertise in the area of AI and machine learning and data science and so on. But we also need expertise in terms of system theory, in terms of the graph theory, the applications, in terms of feedback control, and so on. Moreover, we need the domain expertise. We need people that know about power systems. We need people that know about water systems. Or we have to learn those techniques. And finally, we need the social component and the economic perspective, which I think is actually very important. So at the KIOS Research and Innovation Center of Excellence at the University of Cyprus, we have a group that one of the motivations for setting up this center is to be able to address these issues and have expertise from different areas. And we are looking at things like intelligent monitoring, control, management, and security of critical infrastructure systems like power systems, like transportation, like water systems, and communication, and recently also in the healthcare area. So what I'm going to do next is talk a little bit about some of this research, and more specifically, I'm not going to go into the details. I'm going to give some references because there's no time to go into the details, but you will get an idea of some of the issues that can be addressed. So, for example, if we're looking at in the area of sensor fault detection and isolation, for the case of multiple sensors, what we see is that in a system like this, where you have many interconnections and many systems that are affecting each other, what we want to design is this monitoring agent. And this monitoring agent, the idea of detection really is based on looking at what you have based on the data that you're getting at the time, compare that to the model that you have, as well as the neural network that has learned something, and combine the two, and the difference between the two is what is called the residual. So if the residual is below a certain adaptive threshold, with the adaptive threshold being calculated based on the uncertainty indications that you have, then you can obtain what are called analytical redundancy relations, which are 1 or 0. Has the system exceeded has the residual exceeded the adaptive threshold or not? And if yes, then you get a 1, otherwise you get a 0. So that in order to get an idea, a key thing here is the adaptive estimator, which has a combination of the model as well as the neural network and some filtering methods in there. So the mathematics gets messy, the proofs get messy, but it's important to know what is behind this. And then once you have this, then you look at all, so you have, in the end, you have a lot of ones and zeros, and you have to decide, based on these ones and zeros that I get from all the different components, whether the system is operating healthy, or is healthy or is faulty, and where the faults are. And then the next step is to do the isolation. So the isolation is you have a table, and based on these ones and zeros, you decide which are the possible faults that may happen. So sometimes you can get a unique solution. Sometimes you can get two possible solutions. It's either this or this. But even that information is important rather than not knowing nothing at all. Based on this, we were able to obtain some theoretical results about the robustness, in other words, the ability to do this with minimum false alarms, and the ability to the sensitivity analysis in order to be able to be sensitive to faults. And I'm providing here some of the references in this area with some of my colleagues and postdocs and PhD students. The other thing that I wanted to mention is the area of fault accommodation. So the usual timeline is that the system may be healthy for a long time, for 1 or 2 years. At some point, some component fails, and we don't know when it's going to fail. We don't know what type of failure it's going to be. And the idea is to be able to detect it. So there is some delay maybe between the time that it occurs and the time that it's detected. After that, you have a period where you're trying to understand what type of fault it is, whether it's a sensor fault or an actuator fault, or what type of sensor fault. And finally, you have the fault accommodation, where you're trying to address the problem. So in the case of multiple faults, then you may have this timeline. They have many faults going on at the same time. It gets a lot of overlaps. The other thing is sometimes you're interested in preventive maintenance, which I haven't talked about, but this is also a very interesting area. You don't have to wait until a sensor is faulty in order to fix it. You can try to predict that. So this is another area, and this is also something that is attracting a lot of attention, especially from industry. So in order to do the accommodation, so in this case with the sensor fault accommodation, what we have is we have the nominal controller, and once we detect a fault, we augment this nominal controller with a neural network-based controller, which is actually trying to retain the system. Maybe the performance would not be as good as without the fault, but at least it's operating safely. So this is this result. The other area that we are working on is the area of event-triggered learning-based fault accommodation. So event-triggered is related to the communication. So instead of the controller and the software and the hardware communicating all the time, it makes sense to communicate only when there is a need to communicate. So in other words, you want to send the information if there's some new information that needs to be sent. Otherwise, you don't send the information. By not sending information all the time, you reduce the communication burden, you save battery life, and something that also that is important that we don't pay a lot of attention is that the less you communicate, the less of a risk of a cyber attack, because every time you communicate, you're sending information that may be used. So this event-trigger communication is an important area, and when you combine it with learning-based methods, you can obtain. So you can see here in the yellow, that's where the event triggers. So you have the controller. Before it sends to the subsystem, it goes through an event trigger, and then at the sensing level, instead of the sensor sending information to the controller every time. So think of an Internet of Things online sensor that instead of sending information continuously or every second or every 5 minutes, it sends information only when there is a need to send information. Now, when is the need to send information? Of course, in order to implement that, you need to have some basic software, computational component in the sensor. But the idea is that if the difference between the current measurement and the previous measurement is less than something, which is what this is here is saying, then you don't have to send. So this is kind of an agreement. And also with the actuators, you can do the same. If the difference between what you sent previously is similar, then you don't have to send. So this idea is, of course, there's a trade-off. Now, if the less information, so ideally, the way it's going to work is that when there is activity, if there's fault, if there's a large tracking error, then there's a lot of communication in order to solve the issue. And when there is nothing going on, then there's hardly any communication. However, if we lose communication, then the other guy assumes that there's nothing new going on. So when there is a communication fault, that is going to create a problem. So you can address that by saying once in a while you have to send information to let the other guy know. So these are some of the ideas. Another area of research that we worked on is data streaming. So data stream mining. So this idea, in the case of active learning, and the idea is that how do you choose the input in order to have some certain behavior, in order to be able to detect things. So this is one of the things that is important about faults and about malicious attacks is that unlike the situation of healthy data where we have a lot of it, in the case of faulty data, we don't have a lot of it. So when you think about training, you may have 99% of the data being healthy and less than 1% of the data being faulty. So when you're trying to learn, this creates a bias, which it's a big problem. And people have been trying to address this issue with some of these rebalancing methods and so on. So this is a step in that direction. And we have used some of the techniques like Siamese neural networks in order to be able to do that. And this shows some results. And finally, I wanted to talk a little bit about cyber-physical security. So cyber-physical security, I think, is a very important area. It's going to become more important in the future. And I think this community has a lot to contribute in this area. The more I learn about it, the more critical I think it would become. I think a lot of the people claim that a lot of the, even at the national level, the warfare would be at the cyber security level rather than actual fighting. And I think if this is something that is becoming very important. When you have this large-scale cyber-physical systems, how do you distinguish between uncertainty, between faults, and between malicious attacks? So on one hand, it might be just regular modeling errors, or it could be some faults in the sensors, which may not be critical if you can detect it. On the other hand, it may be an attack on the system, which means there's a person behind it and trying to hurt the system. How do you distinguish? So this is one area that we are working on. So the early detection is critical. And the other thing that is important is how much does the attacker know about the system? So usually, we kind of assume that the attacker doesn't know anything about the system and just is able to take information and inject something. But a lot of the times, the attacker may actually know some of the dynamics of the system. So again, the dynamics of the system come into the picture in addition to the data-driven methods. So this gives you an idea. So the attack can be at the level of between the sensing and the controller. So the controller gets the wrong information, okay? And if the controller gets the wrong information, then it can make the wrong decision, which is or it could be at the level of the actuator, which means that the actuator is giving the wrong decision to the system. So a lot of these techniques are based on the idea that the attacker is smart enough in order to inject enough misinformation into the system to create trouble, but at the same time not to be detected, because if he puts a large signal, then it's going to be detected by other techniques like fault detection and so on. But if they put just enough in order to be able to cause trouble, so this is the objective from the attack viewpoint, and the defender is trying to defend against this. So one of the analyses that we did is on security vulnerability analysis to see what type of attacks can actually be hidden from the defender, from the usual detection. And then we also developed something called a backward in time attack detection policy, where unlike the predictive, where you look forward in time, in the case of an attack, you want to look backward in time in order to be able to see whether the attack came from, whether it's an attack or whether it's kind of the nominal system dynamics. So this is where this idea is coming from. Okay, so I have a couple more minutes. So let me just wrap up. So I have been talking a lot about cyber-physical world and cyber-physical system, where we have the cyber component and the physical component, the physical parts and the cyber part. In reality, I think we need more components than this. And another component is the humans, the social component, which make a big difference on how things are operated. You can have the best intelligent transportation system, but the humans have a key role. So in every component, in every application, the social component is also as important. So instead of saying cyber-physical system, we can think of cyber-physical social system. In addition, I think, especially with climate change, we also have to think about the impact of these techniques in the long term, not only in the operation. So the objective function needs to take into consideration the social component as well as the environmental component, which is something that for a long time, when we talk about performance of intelligent transportation or performance of water systems, we don't really consider the long-term effects because it may be 20, 30, 50 years down the road. So this is something that is not. So this is something that we have started to work on, especially in the area of smart water systems, where we think of not only the cyber and the physical part, but also the social, the policymakers, the utility operators, the customers, and how they react to some of the algorithms that we developed, as well as the environmental issues that are even that are longer term. So this is kind of a diagram that has all the different components from these four areas. So I think if you want to look at these large-scale systems, you have to look at not only the cyber and the physical, but also in the long term, the social and the environmental. And this is this system on smart water system is actually part of an ERC synergy grant, which I'm very happy to be part of. We are working with some people. So this is this project, the Water Futures, is ERC synergy with the title Smart Water Future, designing the next generation of urban drinking water systems, which includes people with backgrounds in machine learning, in automation, but also economics and also water engineers. So this is looking at the different components all together in the long term. So this is a very exciting project that I'm involved in, and with some colleagues. Some of you already know Barbara Hammer, which is from this community. So, in conclusion, before I lose my voice completely, so the building of resilient societies is a key challenge in the years to come. I think we cannot just wait until the next big thing comes and we're not prepared for it. At the same time, we cannot prepare for everything, for all the eventualities. So we have to choose where, and this is going to cost money, but I think more important, we need smart algorithms. And I think these smart algorithms for resilience is where this community can dedicate a lot of effort. The other thing that I think is very important is the combination of modeling aspects in AI and in machine learning. I think there's not enough of it. And I think we need new ways to do that because we cannot just ignore the dynamics and just think of it as a black box. And I think the two together is it's very important. The other thing that I think is critical is for AI to be looking not just in algorithms and data, but think of the application behind it. I was talking with some colleagues at MIT, and they were telling me that about 65 to 70% of the incoming class in engineering want to study computer science. And this is true for other Ivy League schools, and it's true for many areas. You know, in the United States, students can choose their own major. And I think that's a problem. And I think this is a problem for the next generations. We need people that know about power systems, they know about water systems, they know about transportation. We cannot just have people just know how to write algorithms. And I think even the AI people, it's very important when they get some data to try to understand what the data means. So the application behind the data, if there's one message that I would like you to remember, is that the application behind the data is very crucial. And it's very crucial not only because it's going to help you design algorithms better, but it's very crucial that you work on applications that you really care for, not just because AI can be useful or can be harmful depending on what we use it for. So it's very important for researchers in our field to care about the application and how your algorithms, your ideas are used. And finally, the concept of having the human in the loop and how that affects everything that we do. So this is also an important component, as well as the environmental component, which is a little bit longer term, but also very important. And in closing, I would like to acknowledge the several colleagues, students, PhD students, and postdocs that have contributed to the ideas that I presented. Some of these students and postdocs are now faculty in universities around the world. I have learned a great deal with working with them, and I really appreciate their friendship and collaboration. And also, I would like to acknowledge the funding agencies, especially the ERC and the EU widening teaming project that has allowed me to work on this research. And I would like to close with a quote by Rabindranath Tagore, which is an Indian poet. It's actually the first Nobel Prize winner in literature outside of Europe. He got the Nobel Prize in 1913, and you can read it. You can read what it says. So, thank you very much for your attention.
Thank you very much, Marius, for the very interesting and inspiring talk. So I would like to invite a few questions. Any question? Yes.
Thank you for the talk, Mario. I have a question for your page 17, just meant for discussion. Could be useful for other listeners. It's about the architecture. Then you have, in page 17, you have sensory and modules. You have AI, local actuators, then you have local monitoring agents, and I wonder whether those resources are genetic determined. If you do, then do we have a government in the brain so that knows everything? You should do this and you should do that. You do sensory, you do motor, and another you're doing monitoring, and what's the criteria of monitoring. During the workshop about the AI and the governance, some people were talking about altruistic AI, and whether the value should be in the AI. So that's my question. It's not easy, but you can try.
Yeah, it's not an easy question. So in this diagram, the neural network would be both in the K, in the controller, and in the monitoring algorithm. And in the idea by the monitoring algorithm is to not to monitor, of course, the people, but to monitor the system for faults so that we can prevent something worse happening. So this is the idea of the monitoring agent in the framework that I am talking about here.
Do you think there is a government in the brain?
Yeah.
A government, like a humongous?
No government here. Yeah.
Okay. So any more questions?
Yeah. So,
Yes, please.
yeah. Okay. Thank you very much for the great talk. So I was very glad that you emphasized the importance of including social science and domain experts and all kinds of stakeholders. So could you share with us your experience and what would be the good, effective strategy to establish a meaningful connection between technical side and the more social science side? Because some of the tools we use are very technical and inaccessible to people who are more familiar with social human stuff. In the meantime, we ignore grossly the details of human individual complexities. So could you share with us your experience, how to do that better?
Yeah, that's a great question. So, I mean, it's not easy, but I think this is something that we will see more and more. Already in the new calls of the European Union, some of these calls for AI and learning and things like this actually require you to have people with social economic background in the team, or to have legal experts on some of these issues. And I think this is very important. So when you start talking about some of these big issues, I think you need to involve people that know about economics, that know about cognitive systems, how humans react to different things. So in our project on the water systems, we have specific tasks to discuss with the water utilities in order to see what is accepted from them and what is not. Another thing that I think is very important is there are some living labs that, which is a way to get the people involved and to see how they react. Questionnaires. So these are different. The way we prove things in our field is mostly simulations or proofs or things like that. The way that they prove things, the social sciences is more like questionnaires and things like that. So I think these need to come together and in order to, and I think this is a very important component.
Okay, great. Thank you very much.
Thanks. I guess we have the last question.
Okay, it's more of a comment. So thank you very much for the very interesting presentation. You started by mentioning high effect, low probability events, and I just want to mention that it's mostly in the US now. There is a big NSF grant that combines people in geosciences, meteorological sciences, that especially kind of trying to deal with, and your description, kind of your presentation shows that we need, usually what these people do, and I'm a little part of that grant, is we take into account the natural disasters. But you're absolutely right. We need to take into account the man-made, so to say, disaster like cyber attacks and everything. And maybe there should be more collaboration between these geoscientists, environmental scientists, and the groups that you're working on. And thank you very much.
Thank you. I completely agree. I couldn't have said it better. Yeah, I agree with your comment.
Okay, so great. So let's thank Marius again. Thank you very much.